So far in this course, we've been building up a lot of really powerful tools. We've seen different kinds of data structures. We've seen different classes of algorithms. We've seen ways of putting those together to do interesting things, solving problems. And one of the things we might want to do now is just step back for a second and ask, so what are we trying to accomplish when we design a program, a piece of code? What are our goals? And typically there are two. The first and most important one is we want our program to return correct answers on all legal inputs. And all legal inputs. So if we're defining a function that is to apply to integers, we want it to work on all values of integers. Or if there's a particular range, we want to specify that as part of the specs. So our first goal is to have code that does the right thing. It computes the right answer. Second goal can often also be, though, that we want it to perform its computation efficiently. Typically, one is more important. But there are times when that second point is also critical. For example, if we've got a program to detect collisions in aircraft or to do real-time control of traffic signals, we need it to be very efficient to ensure that it can respond before something happens in the world. As a consequence, sometimes two is really crucial. But even in cases when one is most important, it is still valuable to understand and optimize efficiency. So even if we've got code that computes the right answer, if we've got alternatives, they're going to give the same answer, but one's more efficient than another, we'd like to know about that. So, that leads us to this question of what we call computational complexity. And here we're going to do a somewhat informal version of this, but to give you a sense of how you can begin thinking about computational complexity. So what does it mean to say how efficient is an algorithm? There are two questions we can ask. We can ask how much time is it going to take for the program to run? And we can ask how much memory is it going to need inside of the machine in order to do the computation it wants to do. Again, typically we're going to be most interested in this one, the amount of time. We'll see that we can also worry about memory. And for some really big problems, memory is crucial, but in general, we're going to worry about time. How long does it take for the program to run? Even there, when we start thinking about that, we want to be careful. We want to balance sort of minimizing computational complexity with conceptual complexity. And what do I mean by that? I'd like to keep my code clean, simple, easy to understand, so that if I come back to it a month from now, a year from now, I still understand what the code was written to do. If somebody else looks at it, they can understand what the code was intending to do. And I say that because sometimes one can find interesting tricks one can play to get a little bit more efficiency in the code, but it makes the code much harder to understand. And we need to balance that. There's no perfect balance, but in general, I'd prefer to have code that's still easy to understand, and having done that, have it be as efficient as possible, than to jeopardize the code just to gain a little bit of efficiency. We're going to want to make sure that our code is still clean, but we do want to worry about how do we minimize complexity. And the complexity is typically going to be in terms of how long does it take something to run. Okay, so now we could say, given a function, we'd like to answer the question, how long will this take to run? So what are our choices? Well, a simple choice would just be run it on some input and time it. That, of course, has several problems. The first one is, it depends on the speed of the computer. The second one is, it actually depends on the specifics of the Python implementation. Depending on which version you're using, you may get slightly different answers. Both of those aren't great. And the third one is, of course, it'll depend on the value of the input. If I've got something that's a recursive function, changing the input will lead to different amounts of time. So how do I get rid of these factors? I want to be able to make general statements about complexity. Well, for points 1 and 2, I can avoid those by measuring time not in terms of actual elapsed time, but in terms of the number of basic steps that the computer executes. We'll come back to 3 in a second. But we're going to start with thinking about how do we avoid 1 and 2. And for that, we use what's called a random access machine model. We're going to use that as our model of computation. What does that say? It says the steps are executed sequentially. We're not running in parallel. And the second assumption that model makes is that a step is an operation that takes a constant amount of time. And for that, we're going to assume assignment, comparison, arithmetic operations, and accessing an object in memory all take a constant amount of time. You might quibble a little bit. You say, well, maybe multiplication is a little bit more expensive than addition. But as a first pass, this is a pretty good approximation, that all arithmetic operations are roughly the same amount of time, comparisons, assignments. This last one here might surprise you, and we'll come back to that later, but in fact, we can set up our system so that indeed getting to any point in memory is going to take a constant amount of time. The advantage of this model is it says, I'm removing the aspects of the machine. How fast is my machine? What kind of Python am I running? And I'm able to just focus on counting the number of basic steps that I have to execute in order to compute a function. So that removes the first 2 points where I had some concerns. For the third point I'll remind you is, so it depends on the value of the input. Here we're going to measure time not in terms of a specific input, but in terms of the size of the input. And that'll make sense in a second as we walk through it. Now, you might first say, well, okay, even if I'm talking about the size of the input, might the complexity not still depend on the value? Let's take a little example. Here's a piece of code to linearly search a list. This is trying to see if a particular element is in a list. So what does it do? It iterates over the list for an E in the list. And for each one of those elements of the list, it checks to see, is it equal to the thing I'm looking for? If it is, I'll return true. And if it isn't, I'll return false. All right, nice simple piece of code. Here's the problem. The problem is that I could try and measure the complexity of this code in terms of the size of the list L, which makes sense. That's the thing that's likely to change. But the problem is that if X happens to be near the front of L, it's going to return true almost immediately. On the other hand, if X is not in L, then the code's going to have to go through all of the elements of L before it can return false. And so it's going to give us different answers depending on the specific choice. And that's not what we want. We need a general way of measuring complexity. So what we're going to do as a consequence is we're going to think about what are the different cases under which we can measure complexity. Well, the first one would be what we could call best case. It's the minimum running time over all possible inputs of a given size. So for all possible lists of some length, for example, what's the best case I could see? Well, for linear search, the answer will be constant. It would be independent of the size of the inputs. In the best case, because it would be the first thing I look at. That's not very helpful. An alternative is to look at the worst case. What's the maximum running time over all possible inputs of a given size? And there what we see for linear search is this is going to be linear in the size of the list. It's going to take some number of steps that depends on how long the list is. If I double the list, the worst case is going to double as well. That may be more useful to me. There's a third possibility, which is to use the average case or expected case. That is, just average the running time over all possible inputs of a given size. And that might be more effective in terms of thinking, on average, what do I expect to see? I could even be clever. If I know that my inputs don't come uniformly distributed, they're not all equally likely. If I have some knowledge about how likely an input is, I could even take advantage of that to do my averaging. So an average case, in some sense, for practical purposes, is kind of nice. But in fact, what we're going to focus on is the worst case. It's sort of an upper bound on the running time, and it gives us a sense of what happens in the worst possible case for different kinds of algorithms. And in particular, it's going to allow us to compare different classes of algorithms in a kind of nice way. Okay, so now I'm saying I want to measure basic steps. I'm going to do it in the worst case. Let's see how we might try and do that. And let's look at an example. Here's our old friend factorial. Right, little procedure that's going to compute factorial of n. This is a little iterative loop, sets answer initially to 1, and then it runs through a while loop. As long as n is bigger than 1, it multiplies n by answer and binds answer to that new value. It decreases n by 1, and it keeps going through the loop until it's done, and then it returns an answer. You've seen this before. Let's think about how do we measure the complexity here. So we want to count the number of steps. Right, so what have we got? Well, here's the first one, and that's basically one step, that assignment statement. We said that was one of our pieces of our model. Now, inside the loop, what do we have? Well, for each time in the loop, I've got to do a test. And this times equal is actually two operations. It's a multiplication and an assignment. And this minus equal is actually two operations. It's a subtraction and an assignment. So inside of the loop, I go through 5 steps. And then what do? Well, I go through that loop multiple times. So I do 5 steps, and then I do 5 steps, and then I do 5 steps. And in fact, we know we'll go through that loop n times, whatever the value of n is. So there are 5 n steps to go through the loop. And then finally, I've got 1 for the return. So I could write a little expression for this. It says that the number of basic steps I execute here is 5n plus 2. Do we really care about the 2? Well, clearly not, because as n gets large, it gets irrelevant. This really turns into an expression that says it's 5n steps. Again, I'm not worried about tiny differences in terms of milliseconds or something. I want to know, how does this algorithm behave as I make my arguments arbitrarily large? And so basically, This has 5n steps that we need to execute. All right, I got rid of the 2, but what about the 5? Do I really care about the 5? And I'm going to argue that in general we don't, that those multiplicative constants are not relevant when comparing algorithms. To see that, let's look at a different example. Here's something we saw before. This is trying to find square roots. Square root of x within some accuracy epsilon. I'm not going to go through the code in detail. We simply set up a step size, we get an answer, and we've got a little while loop that runs through looking at different values of answer. So it starts at 0, increases it by a small amount, a small amount, a small amount, and it keeps trying it until it finds an answer that's close enough, in which case it returns it. If we were to call this procedure with x equal to 100 and an epsilon of 0.0001, it's going to take about 1 billion iterations to get through the loop. Now, inside the loop, there are actually about 8 steps if we count them carefully. So you could say it's about 8 billion operations, but it's 8 times the number times through the loop. In this case, the number times through the loop is about 1 billion. Now, let's compare that to bisection search. We saw this before. This is a bisection way of trying to find the square root. Remember what it said we do. Given a number, we look at a low value of 0 and a high value, let's assume it's big enough, of x. We pick the middle point, we check it. If it's the answer, close enough to the answer, we're done. If not, we decide whether the real answer lies between that midpoint and the high number, or between the low number and that midpoint, and then we do the same thing. And we keep chopping it down. If we call this procedure on the same arguments, 100 and that same epsilon, 0.0001, it's only going to take 30 iterations through the loop. Now, it turns out in this case there are about 10 steps within each iteration, as opposed to what I had in the previous case, which was 8. So a few more steps in the iteration, but it's really the number of iterations that matter. 1 billion versus 30. Hey, I'll take 30 any day. So what we're really saying is, do we care whether it's 1 billion or 8 versus 1 billion when we're comparing it to whether it's 30 or 300? And the answer is no. What we really care about is the growth in the size of the problem. It's the size that matters, and so those multiplicative factors really don't concern us very much. And what that then says is, given that it's the difference in the iterations through the loop that matter, we're going to drop the multiplicative factor. It's probably not particularly relevant. And so we're going to focus on measuring complexity as a function of the input size. We'll focus on the largest factor in whatever expression we write that captures the number of basic steps, and we're going to be mostly concerned with the worst case scenario.